The resolving vectors, and in a way it's exactly the same as projecting vectors, but in a more practical way. So dynamics problems, we tend to break it up into components, horizontally and vertical. It just makes life easier to study motion when we just look at things that are happening in a straight line. Those two directions are then resolved into one vector, which then can describe the whole situation. Here's a very simple example to give you an idea of what's going on. We've got a plane travelling south, velocity of 100 kilometres per hour. It's got a tailwind of 25 kilometres per hour. What's the plane's resultant velocity? There's our plane, but then there's this wind blowing them at 25 kilometres per hour. Now, the plane still says I'm going at 100 kilometres per hour, but someone on the ground looking at them looks at that plane, and to them it looks like they're going 125 kilometres per hour. So that's the result of the two speeds there. Okay, now here's one in two dimensions, same problem, but this time our wind's going in a different direction. So there's our plane still going at 100 kilometres per hour, but now the wind is going 25 kilometres to the left or easterly. So the result of that on the ground, if we were to look at them, it would look like the plane's going at that angle, and it would appear, bit of Pythagoras, we could work that out, that it's going at 103 kilometres per hour. But that's the general idea. When we look at dynamics problems, it's actually the forces we're interested in. We start with the forces in mass. And force is a vector. Force is a vector because it has a magnitude and it has a direction. And then the two key things of a vector. So say we've got these three forces. The components, 3i, 2j for the first force, next one 6i minus 4j, and the third one 2i minus j. And we want to find the result of all these forces. What would it look like? You've got to remember, resultant force is not an actual force that exists. It's the result of all the other forces acting together. And so here, it would appear that we've got this force happening, 11i minus 3j. Let's have a look at this one. A tractor is pulling the barge, maybe the scale's not great, the tractor is pulling the barge along the canal with a force of 400 newtons. What's the component of the force in the direction of the motion? So what we're really doing is we're saying, hey, if we were to project this force, what's the component horizontally? So really we are finding the projection of the, well, I've called it T for tractor, the force in the T direction, if I was to project that horizontally, so B for the barge. Now, we saw earlier that that would be the same as the magnitude of T times the cosine of theta times the unit vector in the direction that we're travelling, which for us it's just the I direction, and we get 400 cos 14, which is 388. I'm only interested in the magnitude, so there it is, 388 newtons. Now, let's look at something a little bit more interesting. So we have a particle of mass 5 kilograms sitting on this plane, plane's at 30 degrees. We will talk a lot more about different types of forces next year when we look at this stuff in Extension 2, but this problem has certain forces acting on it. Anytime something slides along a plane, you have a frictional force or a resistive force acting in the opposite direction to which you're travelling. So this is the 15 newtons here. We also have a gravitational force acting down of 5g, mass times gravity. And there's this third force. Whenever something's in contact with a surface, there's another resistive force acting in the opposite direction to the surface. So there it is, perpendicular to it. They're the forces acting on this particular particle. What I want to do though is resolve them into not horizontal and vertical. In this case, I'm going to resolve them down the plane and perpendicular to the plane. What I said before was we do things horizontally and vertically out of convenience, but you don't have to. You just pick two directions that are perpendicular to each other. And in a problem like this, it makes more sense to do it down the plane and perpendicular to the plane, because when you do that, some of the forces disappear. So if I'm going down the plane, there is no force of R, because it's purely in the other direction. You couldn't project. Well, if you did project that vector on the plane, you just end up with a single point. So my gravitational force here is the only one that's not in either of those two directions. So it needs to be resolved into those two directions. The force that you're resolving turns out to be the hypotenuse of a right angle triangle. And so I draw up that right angle triangle with the other two sides being in the same directions, or parallel to, being parallel to the perpendicular ones that I've chosen, in this case down the plane and perpendicular to the plane. So there's my right angle triangle. Bit of geometry, I can work out where 30 degrees would sit in that triangle. It would be down here. That angle's 30 degrees. So if I now resolve forces down the plane, I have this component of gravity. So I'm projecting that vector. The quick way of doing it is I just look at it and go, is that the opposite side or is that the adjacent side? The angle I'm referring to here is 30. So that's opposite. So I know it's going to be the hypotenuse, in this case 5g, times the sine of 30. So that component will be 5g sine 30. There's another force, 15. It's in the opposite direction. One of those has to be negative. It doesn't really matter which one. So I've made the resistive force negative. You tend to always make resistance the negative force. So 5g sine 30 minus 15. Let's now work out our force down the plane. Substituting in 5, g, we'll assume gravity is 9.8, sine of 30 is a half, we get 9.5. They ask for acceleration, not force. Force is mass times acceleration, so it's 5 times a. There's my acceleration down the plane, 1.96. Now the reaction force. Let's now do perpendicular. Let's have a look at everything perpendicular. We have that reaction force we're trying to find, but there's also this component of gravity. It's the adjacent side, so that must be 5g cos 30. And again, they're in opposite directions. I'll make one of those negative. We should now be able to work that out. Now, how did I know that force was 0? Because this is the result of all the forces. And think about the thing, it's sliding down. It's not jumping off the plane, it's staying on the plane. So the result of all those forces is nothing, because it's not going up, it's not going down, it's staying in that direction. So I know that is 0. 5g, but cos 30 we certainly know that's root 3 on 2, and we can get that our resistive force is 5 root 3 on 2 g newtons. Alright, so there's a bit of a taste of dynamics.